All right. Hello, everyone. Let's go ahead and get started, please. I hope you all had a great weekend. I wanted to take a few moments at the beginning of class just to talk about what's going to be coming up in the next week or two. I would love to show that to you on Canvas. Unfortunately, as you're probably aware, Canvas is not working right now. So I wasn't able to make my regular weekly announcements and post all the stuff that I usually post on Mondays. I have it all ready to go, and I'm going to post it as soon as Canvas will let me post it. So hopefully later today or tomorrow I will make the usual weekly announcements and let you know what's coming up in the class this week. But the important thing that I wanted to make sure you all were aware of is the fact that our next exam is coming up next week. So 1 week from Thursday, we're going to have exam 2. It is only over the material that we've covered since the previous exam. So that's modules 4, 5, and 6. That's the material that you're going to expect to see on the exam. And just like we did for the previous exam, next week Professor Nuri is going to be running an exam review session during this class period. So 1 week from today on Monday, we'll have our exam review session. I have a lot of exam practice problems and stuff, like I said, ready to post. I just can't do it since Canvas is down, but I will have those up within the next day or two. One other announcement that I was not able to post to Canvas, but I want to make sure everybody is aware of, is that we finally, after many repeated badgering emails to the department and the School of Engineering, we have a date for our final exam. So it is on December the 12th from 3:30 to 5:30 p.m. So if that's something that I know students have asked me about that and I haven't had the answer, I finally have the answer. I will post that to Canvas as soon as I'm able to. But I also just want to remind everyone that we drop your lowest exam grade, which means that if you do well enough on the first 3 exams and you want to drop the final, that is all right with me. I don't have a problem with that whatsoever. But students have been asking me about that final exam date, so I just want to pass that along. Once again, that is December the 12th from 3:30 to 5:30 p.m. is when the final exam will be for this class. Any questions about logistics or exam stuff before we hop into today's topic, today's material? All right. Great. So today's topic is the last one that we're going to be covering before the next exam, right? So this is the last topic of new material. And I just kind of want to start out by, giving fair warning about this one. You may have already heard from TAs or other students who have taken this class in the past that this is a tricky topic. And that's correct. I would say that's accurate. Recursion is a fairly tricky topic. It's usually named as one of the trickiest topics that we cover in this class, and I think that's perfectly valid. The other thing that I want to say before I hop into it, though, is that it depends very, very, very much on understanding the material from last week. So recursion is based upon methods, which Professor Nuri covered last week, and which you did the studio over last week. If you've been following along and you feel like you understand what methods are doing, maybe not everything, right? But if you at least feel somewhat comfortable with methods, then I think you'll be okay today. If you feel like you're totally out of the loop and methods are still just like way over your head and you have no idea what's going on, I would almost suggest not even trying to follow along today. You would be much better served going back and reviewing the concepts from last week. You are simply not going to be able to understand what we're talking about today unless you have a fairly good grasp of the information that we discussed last week. The good news is we'll review some of those topics as we go along, but I am recording, so if you're still struggling with methods, then maybe just chill for a little bit and come back and review the recording after you've had some time to catch up on methods. And also, please come and talk to me in office hours if that applies to you, or Professor Nuri. We would love to see you in office hours if that's something you're still struggling with. Methods are tricky too, right? So don't want to pretend like that wasn't also somewhat of a tricky topic. All of that being out of the way, let's go ahead and talk about recursion. So the definition of recursion is actually very simple. It's a very simple definition. Recursion is when a method calls itself. That's it. That is the entire definition of recursion. Now, there's a bit more to it than that if you want to do recursion successfully, and that's why we're spending a whole day on this instead of just a few minutes, right? Doing recursion is as simple as having a method call, like we see here, inside of the method. So we see that this method is called factorial, and within inside the method we see a method call to the factorial method. This is recursion. So this section right here that calls factorial, that is what I would say is the recursive call. So I would even go ahead and label this as the recursive case. But that's not all the code that's here, right? There's a little bit more to it, as I said. So let's talk about how we do recursion successfully. And in order to understand how to do recursion successfully, it's important to understand what we use recursion for. The good news is that we use recursion to do something that we kind of already know how to do, which is repetition. So in module 2, we introduced you to repetition using loops, using for loops and while loops. Recursion is also used to perform repetition. And that means that actually a lot of times it's somewhat interchangeable. In fact, you'll see me do a couple of examples today where I write the same code using recursion, and then I do the same thing using a loop. So a lot of times you'll have a choice. Do I want to use loops? Do I want to use recursion? And if it's up to you, pick the one that makes the most sense to you, right? For most people, that probably means loops. That probably means loops. There are some situations, which I will illustrate towards the end of class today, where recursion is a really good natural fit for the kind of repetition we're trying to perform. And that's a big reason why we teach this concept to you now. If you go on to take upper level computer science classes, especially the data structures class, you will start to see recursion pop up all over the place when you take those kinds of classes. As far as this class goes, though, we're just trying to get the basics down. So understanding how to use recursion to perform repetition is kind of our main goal for today. And think about what we think about how our loops work. With a classic for loop or even a while loop, they're very similar. We have a starting point, right? We set everything up first. We have an ending point. We usually write some sort of a condition for that, right? A Boolean expression for that. And then we have the stuff that we repeat over and over and over again. I would argue that those pieces are also here with recursion. The part where we stop is actually going to be this section. So in order for recursion to be successful, just like we want our loops to be successful, they have to stop eventually. The same is true for recursion. So how do we make recursion stop? We use what's called a base case. So this part of the recursive method here is our base case. So even though recursion could happen with just a simple method call to itself, for it to happen successfully, we need to have some sort of stopping point defined. This is called the base case. This is almost always going to be just some known value. So you'll see that we're talking about factorial here, and the base case that we chose is if I'm trying to take the factorial of 0, that will be 1. That's just defined by mathematics, right? I didn't make that up. That's just how factorial works. So our base case is always just going to be some previously known value that we're going to use as our stopping point. And then the recursion, the actual method call, is going to be performing the repetition. So this is the part that's going to be repeating over and over and over again until hopefully eventually we hit the base case. I know I'm making it sound kind of easy, but in order to actually generate the base case and the recursive case, it's important to look at the problem that we're trying to solve and try to decompose it. If I were using terms like we saw from the textbook, I would be looking for the recursive substructure. So I'm trying to take the problem that I'm trying to solve and define it in terms of itself. Let's take a look at how we would do that with factorial, and maybe we should do a little bit of a refresher on factorial since it's not the most common mathematical operation that we use, right? 4 factorial is equal to 4 times 3 times 2 times 1, which is equal to 12, 20, 24, right? That's 4 factorial. And we could do more if we needed to, but it's fairly straightforward. What I want to know, though, if I'm trying to write code for this, right? I don't want to write code that only computes 4 factorial. I want to write code that can compute the factorial of any value that I can possibly conceive of. So in other words, I want to do n factorial. How do I compute n factorial? Now look at this simple example that we wrote out. Do you see another version of factorial somewhere in this line? Like could you pick out another definition of factorial in here somewhere? Do you see it? There's another case of factorial embedded in this line. If 4 factorial is 4 times 3 times 2 times 1, then yeah. 3 factorial would just be 3 times 2 times 1. So I actually see 3 factorial right here. So actually, if I wanted to, I could write 4 factorial as 4 times 3 factorial. And that would be equivalent. Everybody follow me? Well, this is kind of the magic, right? Now if I'm thinking about n factorial, think about what that means. That means that n factorial should be equal to n, right, times n minus 1 factorial. So if n is 4, 4 factorial is going to be 4 times 3 factorial. 3 factorial is going to be 3 times 2 factorial, right? All the way down, so on and so forth, until hopefully, if we've done things properly, we hit our base case. But I think it's important to understand not just what code we need to write, but how this code works. So what I would really like to show you next, and something that I hope you kind of did as you were going through the prep work today, is I want to run this through the debugger and show you step by step what's actually happening when we use recursion to compute factorial like this. So I'm going to go back to my main method here and set a breakpoint right here on line 21. And when I run this through the debugger, I believe Professor Nuri talked about this last week, but it's good to review since I'm a big fan of the debugger, and it can be a little bit confusing to use, especially since you're new to it. We have 2 ways of stepping through our code. Before we talked about methods, the only thing that we used was this one, step over. Now that we're using methods, we've started using step into as well. So step into says, take me to the method that is being called here. Take me to factorial and allow me to step through that. If I click step over, I can show you right now, it won't actually take me to the factorial method. It'll just step over it and compute the result, which is fine. You can see the 24 got printed out down here, so it seems like things are functioning fairly well. But we actually want to see how that happens. So I'm going to stop it and start the debugger again. And this time, instead of clicking step over, I'm going to click step into. And notice that it jumped me to the top of the factorial method that was called. And over here, if we look on the left-hand side, we see there's a window. It's the call stack. This is extremely important thing to keep an eye on whenever you're using methods, but especially when you're using recursion. This is going to keep track of all of the different method calls that take place. So we see the method that's on the bottom of the stack is main. In fact, I would always expect to see main on the bottom of the stack. Why? Why am I always going to see main here? Why is main always on the bottom? Yes?
You always start from the main method.
Yes, exactly. Yeah, the main method is the entry point to the program. So if I have 2 methods in this file, which I do, I have one called main and I have one called factorial. Where do I begin? Well, I begin with the one called main. If I have 100 methods in here, which I could certainly do if I wanted to, which one do I start with? The one called main. And if you don't have one called main, it's going to say, I don't know where to begin. You haven't told me where to begin. I need a method called main so that I know where to begin. So this is keeping track of which methods we're traveling through as the program executes. Main is always going to be on the bottom because main is always our starting point. But as soon as we execute main, we have to now do factorial. So you can see that the next thing that's on here is factorial. So we jumped to the factorial. We can actually see from our variables window that n is 4. So we're going to check our base case. Have we hit the base case where n is equal to 0? We haven't. N is 4. So we're going to keep stepping. We jump down to our recursive case, and this says, okay, the factorial of 4 is equal to n, which is 4, times the factorial of n minus 1, which is 3. That's exactly what this says down here, right? It's exactly what we computed on paper. But let's keep going. Let's keep stepping into our recursive calls. And notice what happens over here to our call stack. I see main on the bottom, and now I see factorial appear twice. See factorial appear twice. Think about what that means. The version of factorial that we were looking at just a moment ago was not over. I cannot compute what the factorial of 4 is until I compute the factorial of 3 first. So the 1 with n equals 4 is just sitting there waiting. That method is just sitting there waiting for us to figure out what 3 factorial is. And once we have that, we can figure out what 4 factorial is. Well, in order to figure out what 3 factorial is, if we continue to walk through the code, we'll see that, okay, n is still not 0, which means that 3 factorial, oops, I accidentally deleted something, I didn't mean to do that, which means that 3 factorial is going to be equal to 3 times 2 factorial. Well, I can't compute that until I figure out what 2 factorial is. So once I step into this method, you'll see again, now I have 3 versions of factorial. Again, they're waiting. So the version where n is 4 and the version where n is 3 are both waiting for the computations to finish before they can finish their computations. 2 is still not 0, so we're going to keep doing recursive calls. We're now at the case where n is equal to 1, which is still not 0. So we'll do one more recursive call. And now take a look at where we're at. We finally hit the case where n is equal to 0. Something different is finally going to happen, right? Look at how many calls to factorial are over here on the stack. We started with n equals 4. That's this one. So this is n equals 4, 3, 2, 1, and finally 0, which is our base case. That's our base case. So we've traveled all the way down to our base case. We now know what this answer is. We don't have to compute anything. As I mentioned, our base case is usually some known value, something that doesn't require any additional computation. It's a simple case, right? So the factorial of 0 is 1. So that means that the answer to this version is 1. But I'm not done yet, right? I have to take that value and I have to pass it back. Or what's the word that we use for pass it back? It's on the screen right now, actually. Heard somebody whisper it. Return. It's a return, right? Taking values and passing them from one method to another, that's called return. So it's going to take this 1 that we hit at our base case, and it's going to return it. It's going to return it up the chain. And if we keep stepping, you'll notice that, oh, our stack finally shrunk, right? The version of factorial for n is equal to 0 is done. It figured out its value. Its value was 1, so it said, here you go, here's your 1. And now I'm back at the case where n is equal to 1. So you can see I got a 1 back. It's now 1, and now I can finally compute this. 1 times 1 is equal to 1. That's not too hard. Okay, so the factorial of 1 is also 1. Notice, every time I step now, my stack is shrinking because I'm resolving all of these. So now I'm at the case where n is equal to 2. 2 times 1 is now going to be 2. I'll pass that back up. I'm at the case where n is equal to 3. 3 times 2 is equal to 6. So I'll pass that back up. Finally, we're at our last one. You can see there's no more factorials left on our call stack, right? This is the first one. This is where we began. And I want to make it very clear that this is always the mechanism of recursion. We always travel all the way down to the base case, and we always end up back where we started at the very end. That's how every single recursion problem that you solve is going to work. Go down to the base case and then work your way back up, completing the computation as you go. Finally, we get 6 times 4, which is our 24, and that is what ultimately will get printed out down here at the bottom. Right? Are there any questions about that process? Because that is so crucially important. I would go through that whole debugging thing again if somebody asked me to. I would explain any piece of that. knowing how these execute is crucially important. Anybody have any questions? So one more thing, I think, well, a couple things that I want to chat with you about for this problem. One thing that you're almost certainly going to see on the exam next week is a chunk of code that is recursive, right? And I'm going to say use the substitution method to tell me what the result of this computation is going to be. So let me show you what I mean by that. We actually kind of just went through the substitution method, but let me define it a bit more formally, right? So that when the exam comes around, you know exactly what you need to do when I ask you to tell me what this recursive code is going to do. So let's talk about the substitution method. When you're doing the substitution method, you are literally pretending to be the debugger, right? So if I want to use the substitution method to compute the factorial of 4, I would say factorial of 4 is equal to, so I'm tracing the code. 4 is not 0, so it's going to be equal to 4 times factorial of 3. 4 times factorial of 3. Now, this we haven't tried to figure out yet, so we need to try and figure that out next, which means this is going to become the beginning of the next step of my substitution method. So we'll say, okay, the factorial of 3 is equal to 3 times the factorial of 2. And now we see, oh, this is another version of factorial that I don't know the answer to yet, so that's going to become the next step of my substitution method. And hopefully you're noticing that we're following the same path that I just showed you through the debugger. But I don't need the debugger. If you understand how methods work and how they execute, right, you actually don't need the debugger to write it out step by step. The substitution method is effectively going to do the same thing. So I'll go ahead and do this until we get to the exciting part, which is coming up here. All right, so now we get to the exciting part, which says the factorial of 0. Well, that's our base case, right? You see it defined here as our base case. So the factorial of 0 doesn't require us to compute anything. We just know that that's 1. But we're not done yet. This is actually the part where we see why the substitution method gets its name. Because now that we have defined the factorial of 0 as being 1, I can take this 1 and I can substitute it in for this expression. Does everybody see kind of where I'm going with this? So now I can rewrite this whole expression as factorial of 1 is equal to 1 times 1. Because I know that this value is 1 from this line here, which is equal to 1. And now that I know what the factorial of 1 is, I can take this value and I can substitute it in here. Correct? So that repeated substitution is just going to keep happening. Factorial of 2 is equal to 2 times 1, which is equal to 2. Now I can substitute in the value for the factorial of 2. Factorial of 2 is, factorial of 3 is equal to 3 times 2, which is equal to 6. And then finally I can rewrite the expression for factorial of 4 as 4 times 6, which is equal to 24. And that is, of course, our result. That is our result. So if you're asked to do the substitution method on an exam next week, perhaps, which, again, you almost certainly will be, this is what I'm asking for. I'm asking you to write out the recursive calls all the way down to the base case, and then substitute those values back in until the final value pops out at the very end. Are there any questions about that process? Be happy to go through that one again if people need to. Yeah.
Is it referred to, is it referred as the substitution method in the textbook during the exercise?
That's what I generally call it, yeah. I'm not sure, I don't remember off the top of my head how deep the exercises go into it, but definitely on the studio and the homework assignment for this week, you'll see it mentioned again. So, yep. Any other questions before I move on. All right, I've got more recursive stuff I want to show you, but before we do, one final thing with this factorial example that I feel like is worthwhile. I mentioned at the very beginning that recursion is used for repetition. We also use loops for repetition. So could we do this using a loop? Absolutely we could. I think that's worthwhile because we can see how all of the pieces are really kind of there. It's just maybe written a little bit differently, right? But all of the actual pieces for computing the factorial are still there. So let's try it. Let's try and write a method that does exactly the same thing as this, but it just uses a loop. And you can see that the way that this repetition works is it checks this base case every single time right away, right? Check the base case. Is it true? Then we're done. If it's not true, then we have to keep repeating. We have to keep repeating. That sounds kind of the opposite of a while loop, right? Where the while loop condition says if it's true, keep going, and if it's false, then stop. So we're kind of writing our recursive statements as inverse while loops in a way, if that makes sense. But let me see if I can show you some more concrete code to help illustrate that point. I'm going to make a method called factorial loop, just so I know I'm using a loop. And inside of here, I'm going to use a while loop. But instead of saying, you know, if you hit 0, stop, I'm going to kind of say the opposite. I'm going to say if it's not 0, keep going, right? So while n is greater than 0, or you could even say not equal to 0, I think would potentially work. Then we need to keep going. But what does keep going mean? That means we need to do some multiplication. We need to do some multiplication. I need a variable to keep track of that multiplication, right? So let me make a results variable. Now be careful with this one. If we were doing addition, I think 0 would be a good starting value, but we're doing multiplication, so 0 maybe not the best starting value for this variable. I would actually suggest that 1 would work a little bit better. And consider the case, what if I plug it in 0 here? What should the answer be? Should be 1. So if I plug in 0 here, my result is going to be 1, and I'll just skip the loop entirely and give you back the 1, right? So what we need to do is return our result down here, and finally within the loop, that's where our multiplication is going to happen. We'll say result is equal to result times n. But we also need to subtract 1 from n every time, right? We need to count down. Notice that in both situations, n starts big and gets smaller as it goes until it eventually is going to hit 0. We are also, of course, assuming that n is positive in this case, which I don't think negative factorials are even a thing that exists. So that's not something we really have to worry about. But there are other cases where negative values may be acceptable, and that's something that we need to consider. For this case, though, consider that we always start with a large value of n and we work our way towards 0. That's true both for this recursive case as well as the case with the loops, right? We start with a large value of n, perform multiplication until we eventually hit 0, and then we stop. Just real quick to prove that it works, though, if I come down here and I change this method call to be the loop version, hopefully I'll get the answer back out. Let's see. Yeah, 24. So here, again, just to put some finality on this particular problem, we've got two versions of computing factorials. This one is recursive. That's the one that you already had. This is the one that I wrote to mimic that recursive approach, but using a loop instead of recursion. And again, if it's up to you, right, I'm not necessarily going to say here that one is better than the other. Pick the one that you feel most comfortable with and go with that. Now on an exam, I might tell you, you have to use recursion, right? But in real life, nobody's going to tell you you have to use recursion, so pick the one that you feel most comfortable with. All right, I'm about to switch to a totally different problem. Last chance to ask questions on this one before we take a look at another one. Great. So I'm actually, this next problem isn't going to be in the practice problems that you had. I made it up to just for us to talk about today. And actually, there's no recursion in this file yet. So you don't have this file. This is only a file that I have, but you're welcome to try and follow along with me. Let's take a look at this first, because what I want to do with this one is kind of the opposite of what I just did. This is a piece of code that uses a loop, and I want to try and recreate this behavior using recursion. So how do I take something that already exists as a loop and do it using recursion? First, let's make sure we understand what this piece of code is doing and how the loop works. The name of the method is countOdd, and I see that the first thing that happens is it creates what looks like a counter variable and starts it at 0. This we call an array, what's that word again? Starts with a T? Traversal, yeah. So we're traversing this array that we got as an input parameter. It's a good vocab word. And we're checking. We're saying if the value in the array is, what is this asking? If it is odd, then I'll increase the count. If it is even, then it just doesn't do anything. So at the end of this method, it should tell me how many odd values are in the array. That is what this code is, I think, successfully doing, but we have a test up here that we can use to check it out. Here's an array that got created. It has 1, 2, 3, 4, 5 odd values in it. So if I say count how many odd values are in this test array, I'm hoping that it tells me that there are 5, and we can run this code real quick just to verify. And yes, there we go, 5. 5 odd values were found. Okay, no recursion in this example yet, but I want to redo this, and I want to not use a loop. I want to use recursion. Before I do, though, I want to point out that there are sort of 2 categories of things that I need to pay attention to. Some things are not repeated. So, for example, this value is not repeated, or this line of code, rather, is not repeated. It's not inside of a loop, so it only happens once, right? But all this stuff is repeated. And that's not unusual. A lot of times when I'm writing a program, there'll be some stuff that I only need to do one time, and there'll be more stuff some stuff that I want to repeat a whole bunch of times. But remember, recursion is only for repetition. Recursion is only for repetition. So if I have stuff in my code that I don't need to repeat, that should not be in a recursive method. And as programmers, it's up to us to recognize that and decide to split it up. So I'm now saying, well, hey, you may actually need to use 2 methods to pull this off. One method that does the non-repetitive stuff, and one method that does the repetitive stuff. And the method that does the repetitive stuff is going to be the recursive one. The method that does the non-repetitive stuff is not going to be recursive. It's just going to be a regular plain old method, right? Like we saw last week. So we're going to kind of combine those 2 concepts together, right? So let's see if we can try and decompose this problem a little bit. Figure out, for starters, what's the where is the recursion here? How do we actually repeat? Every time we go through this loop, right? How is it different from the last time that we went through this loop? Can somebody help me out with that? If I go through this loop, if I take 2 trips through this loop, what's different between the first trip and the second trip? Yeah. The index value is different. The index value is different. So whether I find an even value or an odd value, it doesn't matter, right? After I've checked that value to see if it's even or odd, I move on to the next one. And that's the repetition. And I keep doing that until I've run out of values, until I've hit the end of the loop. So our stopping point, or in recursive terms, what's the stopping point called in recursion again? Base case, there you go. Base case, nice little rhyming word. The base case is going to be based on going off the end of the array, right? Running out of terms to check. So, in other words, if I wanted to try and start the substitution method for this, counting the odd values of an array that looks like this is the same as inspecting this value, asking is it odd or even, right? it's odd. So we know that's going to be 1 plus count odd of everything that comes after it, right? Everything that comes after that value. So everything that comes after it would look like this. Notice that this first value is effectively chopped off. Now that might seem a little bit scary. It's hard to remove values from arrays. We've talked about that, right? So we're actually not going to remove the value from an array. We're actually going to do similar to what this loop does and use a loop variable to help us keep track of our position in the array. But let's start trying to put this together using recursion. I'm going to make this method again. I'll call it count odd with a capital R on the end for recursion, just so I know this is a recursive one. It's going to take in an array of values. Now be careful. I know we're talking about recursion, so the first thing that you might want to do is think about your base case, right? If I is greater than values.length, then, return, oh, I forgot what did I forget here? I forgot something important here. What did I forget? Anybody see what I'm missing? Good quiz review, yeah. The return type, thank you, yeah. There's a word in between static and the name of the method. I accidentally a word. So this should be an int. So it'll tell me how many odd values it can find inside of the array. So, I might try and do something like this. If I is greater than the length of the array, then no odd value. But wait a second, I don't have I. I doesn't exist. So be careful. This is actually a case where we need to do the non-repetitive stuff first and then use another method to perform the recursion. This happens so often that we have a name for it. It's called a helper method. It's a very common technique when using recursion. This method is not going to be recursive that I'm writing. This method is going to kick it over to a second method called a helper method. And there's two reasons why I might want to do this. One of them I've already said, to isolate the repetitive stuff from the non-repetitive stuff. That is one reason why I might choose to use a helper method when executing recursion, when writing something recursively. Another reason why we might want to use a helper method is if I don't have enough parameters to help me perform the task that I'm trying to perform. In other words, I need to keep track of my position in the array, but where does I begin? How do I keep track of I? How do I make sure I is moving up appropriately, moving down the array one element at a time? Well, I will make I here, right? This only happens once. Setting I to 0 only happens once. So I will do that in the non-recursive method. And in my recursive helper method, not only will I have the array of values, but I'll make an int I. I can add this extra parameter, right? If I want to help make the computation easier. Think about what that means when we inevitably have to link these two together. When we link these two methods together, I have to say, all right, after you create I, go down here to this method. What's the term for that again when I say go do that method? Starts with a C. Calling the method, yeah. So when I call the method here, I have to give it two things. I have to give it an array of values, and I have to give it some value of I. So I'll just go ahead and say values and I here. Think about what I've done. This stuff is only going to happen once. So all of the code that only needs to happen once, anything that happens outside of the loop or this loop initialization variable, the loop variable initialization, that's stuff that only is going to happen once. That's going to go in the non-recursive method. I'm then going to call my recursive helper method, and that's the one that's going to do all of the recursive stuff. So if I starts at 0 and I'm moving through the array, I know that I'm done once I gets to the end of the array. That'll be my base case. If I is greater than or equal to, right, values.length, then I am finished. I'll just say 0. If I'm off the edge of the array, how many odd values have I seen? 0. None. I've not seen any of them. Else, this will be my recursive step. First, I have to check and see if the value is odd or not. So if values at I mod 2 is equal to 1, then I have seen an odd value. Perhaps I need to make a variable for it. All right. I'll say, all right, here's a variable to keep track of whether or not I've seen an odd value. If I ask in this if statement if the value is odd, then I'll set that to 1, indicating that I have seen that odd value. And now our last step, which is perhaps the trickiest, is to do the recursive call. Remembering that the recursive call is going to be basically passing this along this value, which we have this 1 plus the recursive call, where I, if it was here before, is going to be moved along to the next index on the next time around. So the way that that would get written out is like this. Count odd r. We'll pass in the array, but the next time I don't want to look at I want to look at the value of I that is next to me, or in other words, I plus 1. I know there are some errors here. I'm going to get back to that eventually. But before I do, let me just take a moment to reiterate once again how this code is working. We're actually going to start here, set up our initial loop variable, and then pass off execution to our recursive helper method. The reason we do that is for two things. One, we want to keep the repetitive stuff isolated from the non-repetitive stuff. So this is the non-repetitive stuff, and this is the repetitive stuff. The other reason why we like to do it is because it allows me to add additional parameters to my helper method that will allow me to perform the computation. So this is doing the same thing as this. You can actually see they look identical, right? Int I equals 0. They're in a different place. They're in a different place, right? Every time we go through, we're checking to see if this is true or not. You can see the base case. Again, it's worded in the opposite fashion, but we're still checking, have I hit the end of the array or not? Within the repetition, we're checking to see if the value is odd, and if it is, then we're adding 1 to our odd value. But actually, this isn't quite correct. There's a couple of problems that I have with this. Does anybody, you can see there's a few errors here. Does anybody know one of the errors that I've made? Does anybody see one issue that they can help me out with, perhaps? So this one, if we look at it, the error is going to say this method must return a result of type int. So I've said that the return value is an int, which means I have to give you an int. I have to. Have to. And nowhere inside of here do I see a return statement. Nowhere inside of here have I said, this is the integer answer. This is the answer that you're looking for. So there's a couple ways that you could do that. One way is to simply do this. This can be kind of confusing to people, although I think more experienced programmers would probably do it this way, myself included. But if we want to break this down a little bit and think about how this is actually working, if you want to write this a little bit differently, I could say something like this. And then on the following line, return result. Think about what's happening. Saying call this method. This is going to give me an integer. I will store that in this variable, store that return value in this variable, and then that's the answer that I'm looking for. We actually have the same problem down here where we need to say return in front of this. Oh, I'm sorry. I made a mistake down here too. Let me undo. This is not recursive. it should say this. This was not recursive. I made a mistake. The helper method should be recursive. That means it should call itself. And I used the wrong version of the method. This should say helper. This is recursion, right? Recursion is a method calling itself. That means the name of the method exists inside the body of the method. That's recursion. So that was me kind of screwing up a little bit. Now that we've done that, I think we're close. I think it's still not quite right, but let's go ahead and test it, and I want to run it through the debugger as well. I'm going to switch this to use the capital R version of count odd. And you can see it's telling me 0. Whoops. It should have said 5. There are 5 odd values in this array, but it's telling me 0. I forgot to incorporate this variable in my result. You can see I counted the one here, but what I really need to do is add that. Make sure it gets added to the recursive call so that I don't lose this odd value that I've counted. If it checks it and it's not odd, this stays at 0, so we don't get any additional values. If it checks it and it is odd, it becomes 1, meaning that we're going to tally it up. I'll run it just to make sure it works, but then before I move on, oh yeah, there's the 5. Before I move on, let's run this through the debugger, because I think that will help greatly for understanding. And then I have one more problem that hopefully we have time to get through before the quiz. All right, I've set my breakpoint here on line 6. I'm gonna go ahead and start my debugger. Now, I don't wanna click the step into button here because there's no method call here. So the step into button is only useful on lines where we have method calls. And the line where I see a method call is this one. So I'm actually just gonna click step over. And then when I get to this line, that's when I wanna click step into so that I can see how this recursive method is going to work. All right, here I am in the count odd R method. You can see that I was in main. Now I'm in my count odd method. I'm gonna set I to be 1. And now I'm going to jump into my helper method, which remember is the recursive method that is going to be doing all of the repetition, all of the repetitive work. Once we go in here, we're going to check our base case. Have I reached the end of the array? That's the same thing we're checking for here. Have I reached the end of the array? We haven't reached the end of the array, so we're going to ask, is the value in the array even or odd? In this case, we can look at the debugger to see that it is odd. So we're going to keep track of that odd value, but we're not done yet. I now have to check to see whether the next value is even or odd. So you can see that we're going to increase I by 1, and the next time we step into this, look at our call stack. This is where we started. This is where we are now. So I'm now looking at the next value in the array. Still haven't hit the base case. Is the value odd? I don't actually remember. It is. It is odd, because it's saying our odd value is 1. Okay, we're still not done though. We still have more values to look at. I is now going to be 2. I think our array has how many values in it? 1, 2, 3, 4, 5, 6, 7 values in it. So we still have a few steps to go. Let me speed along here so we can get to the base case. There's another recursive step. There's another odd value and another recursive step. There's another odd value and another recursive step. We'll get to the base case here eventually. Is this the last one? Do we have one more? Here we go. All right. We have finally hit the base case, and take a look at the call stack over here again. We have our main method. This is our non-helper method, and then the helper method is the one that's appearing a whole bunch of times because it is the one that's doing the repetition. There's one version of this helper method for each element in the array. Do you see that? I hope. Actually, there's one more than that because we go off the edge of the array and then we know we're done. We haven't actually tallied anything up yet though. So on the way back up, we'll start to see all of those ones get accumulated together. And here we go. On the way back up, we'll see that, okay, on the end of the array, there's no odd values, but now we'll start adding them up. And as I keep stepping through, you'll see the number keep getting bigger and bigger until ultimately we hit the very first value and print out our result of 5. There it is. 5 down here at the bottom. This is a more complicated recursive problem than the first one for sure, but I bring it up intentionally. If you're using arrays, odds are pretty good you're going to want a helper method. You will see another example of that in Studio this week. You will see another example of that on the homework assignment this week. So if you're still kind of fuzzy on this helper method business, totally understandable. You'll get some more practice with it on Wednesday in the labs and also on the homework assignment. Any questions right now before I move on to do one more recursive problem to wrap things up? All right, so let me repeat something that I kind of already said earlier, which is that recursion is used to do repetition. I can, and in fact did, solve both of these recursive problems using loops. And if you came up to me and said, hey, Professor Shook, write a method that counts all the odd values in an array, I would use loops. I wouldn't use recursion for that. If you asked me to write a method to compute factorial, I would probably use loops. I probably wouldn't use recursion for that. So what's the point then? Why am I standing up here showing you all this recursive stuff? Well, the next problem, the final problem I want to show you, is an example of when we really like to use recursion. So these first two, if you think loops are better, I agree with you. For solving these kinds of problems, I also think that loops are probably the better tool for the job. But the next problem that I'm going to show you is one that I think recursion is a better tool for the job. And it is a drawing one. So we're actually going to be doing a little bit of drawing with standard draw to wrap things up today. I'm going to look at this graph paper exercise. So the goal is, actually, I think I can go ahead and run this and show you. Yeah, the goal is we start with this blank screen, and we wish to make graph paper, which essentially means drawing a grid, right? Drawing a grid, drawing a whole bunch of grid lines on this. The way that we're going to do this is that we're going to approach it recursively, but instead of just using it to do sort of a straightforward repetition, like our loops do, we're going to do something called divide and conquer. Divide and conquer problems are great fits for recursion. If you take upper level comp sci classes, you'll learn about these problems in more detail, and you'll use a lot of recursion to solve them. It's the standard way of doing it. But let's talk about what I mean by divide and conquer. The way we're going to divide and conquer this problem is we're going to draw a cross. The first thing we're going to do is we're just going to draw one vertical line that splits it in half, and one horizontal line that splits it in half. And then consider that after I do that, I have 4 quadrants, right? Each of which is just a smaller version of what I started with. So I start with the whole window, a blank window. I split it into 4 chunks, and now I have 4 blank chunks, right, that are smaller, but I'm going to draw a cross in each one of those. And that's going to make more quadrants. It'll make 16, right, the next time around. And then I'm going to draw a cross in each one of those. And I'll keep repeating that process until I get the kind of grid that I'm after. So let's go ahead and start writing the code for this. This is our graph paper method. Look at the parameters. It tells us the lower left-hand x coordinate, the lower left-hand y coordinate, and then the size of graph paper that we want. So the smaller this size is, more fine grain we want our graph paper to be. Okay, and actually you can see down here that the initial values are 0, 0, so the bottom left corner of the screen, and the size is 1, so I want to make graph paper on the entire window. So first I'm going to draw one horizontal line and one vertical line, and if you need a refresher on how to draw lines, you can refer to the standard draw API, but there is a method in there called line that will work appropriately. We just have to figure out what these values are. So it wants 2 xy coordinates, one for each endpoint of my line. So the first, let me draw the vertical line first. The vertical line is going to be at our, so if I need to do some math here, right? The vertical line is going to be at our lower left x coordinate plus half of the size, right? Because the full size is all the way over, plus half of the size, so that'll get me my x coordinate. And the y coordinate will go from the lower left y coordinate, which is 0, all the way up to the top, which is we have to add the size onto. So the x coordinate for the bottom is going to be lower left x plus size over 2. I'm making the argument that that will get me to here. The y coordinate is going to be simply lower left y, because I started with this, and I started with the lower left y coordinate being 0, and that's where I want the bottom of my vertical line to be. I also need to compute this top point. So the x coordinate is going to be the same, lower left x plus size over 2. The y coordinate will be different though. It's going to be lower left y plus the size. Let me go ahead and run this and see if it gets me my vertical line. It should just be one vertical line for now. There it is, one vertical line. Now I wish to draw a horizontal line bisecting this. We're going to do the same thing with using algebra based on the information that we have available to us, which is the lower left-hand coordinate and the size of the box, right? So if I want to draw a horizontal line, the x coordinate is going to be the same as the lower left x coordinate that I started with. To get the first y coordinate, we need to go up by a factor of size over 2. So it'll be lower left y plus size over 2. And then for the other endpoints, we have our lower left x value plus the size. And the y, since it's a horizontal line, the y coordinate doesn't change. So it'll just be that factor of size over 2 added on. And now that we've written that line of code, I'll run this again and make sure I have my cross. Here we go. Here's my cross. I haven't done any recursion yet. I simply drew a cross that bisects this box, both vertically and horizontally. But hopefully it should now be very clear why I'm calling this a divide and conquer problem. I'm now going to say, draw a graph paper on this quadrant. 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 I'm going to use recursion to do that. I just need to update all of the values. So let's start with the lower left quadrant. I want to say, now keep going to the lower left quadrant and draw more graph paper. So let's try that next. I'm going to call, I'm going to use recursion. GP is the name of the method. What is the lower left-hand coordinate of this lower left quadrant? Well, it happens to be the exact same as the one we started with, right? This is the easiest one. So we don't need to modify LLX or LLY at all. What is the size of this? So we started with a size of 1. This is now going to be cut in half. Do you see that? The size of this quadrant is half the size that we started with. So I would say size over 2 here. That's it. Let's run this and see what happens with just this one recursive call here. Okay. Goes all the way down, then it drew across here, then it drew across here, then it drew across here, then it drew across here. So I covered one of the 4 quadrants. I covered the lower left quadrant. But we're about to find out why it's called divide and conquer, right? With divide and conquer problems, I don't just have one recursive call. I have multiple recursive calls. I'm going to have one recursive call for each of the divisions that I'm conquering. In this case, I would expect to have 4 recursive calls. One for the lower left-hand corner, one for the upper left-hand corner, one for the upper right-hand corner, and one for the lower right-hand corner. So divide and conquer problems are going to have multiple recursive calls. That is different than the prior examples that we've seen today, right? Let's do the next one. Let's do the upper left-hand corner. So I was looking at the entire screen. How do I get from the entire screen to just the upper left-hand quadrant? This was my original coordinate. I need to go up by size over 2, right? So my y direction needs to go up. My x direction, though, it's not actually changing at all. It's the same. So we'll leave the lower left x alone. Lower left y is going to increase by size over 2, and the size of the quadrant is also going to be size over 2, just like the last quadrant was. And if we add that second recursive call, I might label these as well. This is lower left. This is upper left. So now I've done 2 of the 4 recursive calls, and if we take a look and see what happens, okay, it's going down to the lower left, and then, oh, it's coming back and hitting the upper left now. And then eventually makes it up here, right? And hopefully you can now see where I'm going to go for the other ones. I have to do the upper right-hand quadrant. So that's going to be a shift in both the x direction and the y direction by a factor of size over 2. So lower left x plus size over 2, lower left y plus size over 2, and then the whole thing is going to have a size of size over 2. We can run this one, and now I should have 3 of the 4 quadrants. I might need to take that pause statement out, or it's going to take forever. But it does seem like it's working. Let me make this a little faster. There we go. And then finally, the last one that we need is the bottom right quadrant. So that's going to involve changing the x-coordinate, but not the y-coordinate. The y-coordinate remains the same. So our final recursive call is going to be lower left x plus size over 2. Leave our lower left y, and then remember to scale the whole thing down by size over 2 to get our final graph paper. You don't actually have to pause it. It's fun to pause because then you can see all the recursive, but if you just take the pause out entirely, it'll just go boom, graph paper, right? And you can adjust how fine your graph paper is by looking at the base case. So the base case, what is this saying? It's saying if the size is smaller than some arbitrary value, usually this is smaller than what we can see, then I'm going to stop. But I can tweak this, right? Depending on the size of graph paper I want. If I make it a little bit smaller, it'll go deeper. The recursion will go deeper and make, oh, that's maybe a little bit too much. That's not useful. That's not useful graph paper. But you can do some tweaking here, right? Until you get something that you like. There's lots of stuff you can do with this. You can tweak the colors. You can make each quadrant a different color if you want to. Lots and lots and lots of examples that you can do with this. But the main takeaway of this problem is divide and conquer problems. That's what we want to use recursion for. And it requires not one recursive call, but one for each piece that I am dividing and conquering. All right. If there aren't any questions, then we'll go ahead and get ready for the quiz. Go ahead and put your electronics away, put your laptops and phones away. Give me just a moment here to get the quiz started.